was scheduled, so I guess it wasn't that unexpected. You can try and move this a touch there. So what we're looking at today is chapter 4.1, which my goal is to get that done, and I'm sure I will, based on the other class. And with a bit of luck, we'll also get started on 4.2. And there is only two sections in chapter 4. So this Sunday, chapter 3 and 4 have to be done, right? So that's your schedule. Make sure chapter 3 and 4 homework is completed on time. So we're going to be looking at what's called the Introduction to Probability. It's one of those concepts that we probably are aware of. We just don't formalize it in the way that statistics people formalize it. But there's probably been at least some time in your life where you would say, it's very unlikely that that's going to happen. Or there's a 50-50 chance, right? Could happen, it might not, might, that kind of. When you use phrases like how likely something is or how unlikely it is, you're actually using the language of probability. What we're trying to do here is we're trying to put a number on how likely something is to happen. And the simplest probability in the world is, and we call it an event. So imagine I wanted to find the probability of an event A. So the symbols we use are P for probability of event A. And an event A could be anything that is random, right, unpredictable. And we're going to put a number on how likely this event is going to be. So let's give you the general formula and then actually apply it. It's made from a fraction. The probability is a fraction. The top number is how many ways could event A happen? And the bottom number is what is the total number of things that could happen? So that's a rather long-winded way of generalizing it. So let's give you an example. Suppose I take a normal dice. Sure, you've all seen a dice. And I say to you, what's the probability that I throw the dice and I get the number 3?
1/6.
1/6. Now, if you think, where's that coming from? There's only one number 3, and there's 6 numbers that could happen. Now, what we tend to do with probabilities, and certainly this textbook does it, WebAssign, is that we almost always turn them into decimals. So I'm going to just turn this guy into 2 decimal places. So he rounds off to 0.17. And the reason why we almost always turn probabilities into decimals rather than leave them in fractions is one of the things you might want to do is compare 2 different events, 2 different probabilities. And you might want to say which one's more likely than the other. So if I went and said to you, one of them was 70/35ths and the other one was 16/33s, would you agree it's quite hard to tell which one's the biggest and which one's the smallest because they don't share a common denominator? Now, if I turn both of those into decimals, I should be able to tell which one's the biggest probability, and that means it's more likely to happen than the other event. And quick calculation, let's see what that is. Has anybody got a gut feeling which one of those 2 is the biggest?
Probably 16/33.
Okay, let's find out. This guy here is 0.4857. And the other one is 0.4848, roughly. So would you agree this one here is bigger? But decimals make it easy to decide. Second reason, now and again, you're going to add probabilities together or multiply two probabilities together. And if they're decimals, doesn't it just make life easier because calculators really work well with decimals? And if it's really awkward, weird fractions, adding them and multiplying them is probably going to just add to your workload and make it harder to do. So can I sell you on the idea that probabilities are turned into decimals and there's reasons why we want to do that? Well, that's a beginning. Suppose I said to you, what's the probability that I throw a dice and I get an even number? Well, there's 6 things that can happen when you throw a dice. How many of those 6 things are even?
3.
Agreed. And so that guy comes out as a half, which is 0.5. So if I was a gambling person, wouldn't I gamble on an even number because I'm more likely to win than if I just gambled on a 3 turning up, right? There's more ways to win, essentially. Actually, 3 times more ways to win. So far, so good. Nothing really spectacular. So let's look at the range of values for probabilities. Now, because of the way a probability is calculated as a fraction of the time something can happen, there's actually only a range of values that this calculation can ever truly be. 0, so something that has a probability of 0, is really something that's never going to happen. Does that make sense? That a 0 probability means something is not going to happen. What's the biggest value a probability can be?
1.
And what situation would a probability of 1 be talking about?
It's like, like for the dice example, for like you would say it's like 100% chance I'll get a number between 1 and 6, right?
Right. Yeah. Or it's a guaranteed event, right? It's going to happen, right? Whatever event A is, if its probability is 1, it's going to happen. So if I roll a dice and I say, what's the probability I get a number between 1 and 6? The answer is, yep, it's going to happen 100% of the time. If I said, what's the probability that a politician's going to lie today? Yep, it's 100%. One of them's going to lie. Multiple ones are, but guaranteed one, right? 0, what's the probability that I'm going to win the lottery tomorrow? Because I don't buy lottery tickets,
yeah,
so
0.
it's 0. And at 1, I know, probability it's going to rain in Washington sometime this year. Right? I think that's theoretically it's pretty darn close to 1. Now, sometimes probabilities are also converted into percentages. So if somebody says the probability of something happening is 95%, isn't that an event that's very likely to happen pretty much every time? Not a guarantee every time, but very likely, right? 95% probability. Something with a 1% probability, isn't that a pretty rare event? It's not going to happen that often, right? So if you're playing cards, the chances that you get, 4 aces is tiny, right? The probability of that happening might be 0.5% or less, right? But the probability you get a heart is very high, which you get a great chance if I deal you 4 cards, one of those probably going to be a heart at least, most of the time. Now, anything between that, well, right in the middle, we have 0.5, right? That's a 50%. I've heard people say words like, it's a 50-50, there's an even chance of that happening. That's kind of where they're talking, isn't it? Something that's half the time is going to happen and the other half of the time it's not going to happen. Probably our weather's a bit like that. Isn't there like a 50% chance tomorrow it's going to rain? Now, if you are given a list of probabilities, you should be able to use the fact that they must be between 0 and 1. You should be able to tell which ones are impossible. So I'm just going to give you a random list. So here are a list of numbers and fractions and decimals, whatever you want to call them, various types of numbers. And we're going to go through each one and see whether or not that could be a probability. Could you do a thing and get a probability of 7/4? Too big. What about 1.3 probability? Too big. Great. 110%. Could you have a, right? Do you know those annoying people who says, you're going to give 110% today? You know, how, you know, your football team's going to give 110%. Do you know that drives me up the wall? Because isn't the most you can ever do is 100%? That's, yeah, everything. So that's me. Don't use it. That's meant to say 0.6. Is that okay? What about negative 0.2? Right. So out of that entire list, only one of them was actually a valid probability, a number you could get out of a probability. Are we good? Any questions? Okay. So let's look at what's called, oh, I don't know why I'm using red. Here we go. The complement of an event A. Suppose A is an event, it rains tomorrow. The complement of A, we write it like this, but you read it out loud as the complement of A. It's the event that is the exact opposite of whatever A is. So what's the exact opposite of it rains tomorrow?
It doesn't rain.
Right? So you could say it doesn't rain tomorrow. Couldn't you also, and that's totally valid answer, nothing wrong with that, good answer. Couldn't you also say it's dry tomorrow? And that's essentially the same meaning. If you assume that dry and wet are the only two things that are allowed to happen. Suppose A is your roll of dice, and you get an even number. What would the event, the complement of A be?
Odd number.
You could have phrased it, I like that way of phrasing it, but couldn't you also phrase it not getting an even number? Couldn't you just basically stick the word not at the front of all these, and that would be the complement? That it's not going to rain, that it's not going to be an even number. But sometimes the English language, it's clearer if you kind of write down what the equivalent of not being odd is, in this case being even, right? There is a connection between these two probabilities. Let's pick another one. Let's do A, roll of dice. And I get a 5. Well, the probability of A is very simple, right? It's 1/6, which is about 0.17, right? We did that earlier. Now, the complement of A, well, wouldn't that be not getting a 5? How many ways can you roll a dice and the thing ends up being something that's not a 5?
5, 6.
Do you notice that there's a connection between these two? They're not equal to each other, but there is a connection between them. What do you think the connection between these two is when you look at the probability of a thing and a complement of that thing?
They equal 100%.
Yeah. So they equal 1, or if you want to, 100%. You can sometimes use that to come up with probabilities that might be difficult to calculate if you did them in the way they were asked. Because what I'm saying here is that basically the probability of an event plus the probability of its complement is 1. But if you rearrange that, isn't the probability of the complement 1 take away the probability of the event? And another way of rearranging it would be this way. So as far as mathematics are concerned, aren't these 3 statements really equivalent to each other? They're just different ways of putting them together. Okay. Now, I'm going to describe a kind of more complicated event. And I want you to imagine, although I'm not going to draw the whole thing because it takes forever in the day, but this is going to be a table. 1, 2, 3, 4, 5, 6. Do that guy. Put 1 here. At the top, I'll do a 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. And go 1, 2, 3, 4, 5, 6. And actually, I'll make them green, just to be different. There we go. What this table is trying to describe is what happens when you throw 2 dice, right? So you get 2 dice and you roll them and you throw them. Now, when you do that, there are actually 36 different things that could happen. And I'm going to write them like coordinates. This one here, for instance, would be the green dice is a 1. And where's my red? And the other guy is a 6. And I'm getting color scheme back here. And if I finish with this bottom one, that would be the green one was a 6 and the red one was a 6. Can you see that if I filled this entire table up, can you imagine that there would be altogether 36 different things, right? 6 rows of 6, 36 different things I can have. Just randomly, I'll pick one. This one here. This one here would be the green dice was a 3 and the red dice was a 2. So far, so good. Now, we have a thing called the sample space. And the sample space is a list of every possible event. So in this world, when you roll 2 dice, isn't the sample space 36 different things that could happen? So far, so good. 36 different things that could happen. Now, let me try and give you a puzzle. Let's suppose I roll 2 dice and I add them up. You know, like you play various, you know, the games, board games, you roll the dice and you get 3 and a 2. So you get a 5 and you move your little guy 5, that kind of thing, right? Event A is that you get a total of 6 and event B gets you a total of 7. And we are going to find in a few moments what the probability of these 2 events are. Before I do that, do you think these 2 probabilities are going to be the same? Or do you think one of them is more likely to happen than the other? That's your choices. They're the same, or one is more likely than the other.
I think that one is more likely than the other.
Are you, good answer, because that's correct. Which one do you think is more likely than the other?
The 6.
Okay,
I think
let's
the
think.
7.
So we got both answers. Now, that's good. I like that because it gives us a thought process. If you look at the history of where this came from, do you know that probability started in a very seedy way? In fact, what happened was, I think it was in the 1800s roughly, there was a lot of gambling games like roulette and blackjack and all sorts of other gambling games, poker, whatever the games were called in those days. A lot of different gambling games, rolling dice, craps, that kind of game, right? And people who were playing those games went to mathematicians and said, look, we'll play this game where you roll 2 dice and you add them up. And if you pick the right total, you win money. And if you pick the wrong total, you lose money. What one should I pick so I can win more than the other guy? That kind of thing. I need an edge. I need to know what this is. And probability basically came from that. So let's look at the story and see what these two probabilities are. And I've lost one of my pens. Here we go. There are 36 things that can happen when you roll 2 dice. Agreed? How many of them add up to a 6? Well, let's see if I can find them here. I'm not going to do the colour scheme because it just take too long. Would you agree a 5 and a 1 gets you a 6? Right? So I put a little asterisk. That one gets you a 6. Why am I calling that a 5 and a 1? I should call that a 1 and a 5. I guess it matters order. This next one is a 2 and a 4. 2 3s, right? A pair of 3s. This one here is a 4 and a 2. And this one here is the 5 and the 1. 1, 2, 3, 4, 5 different ways of it happening. So if you roll 2 dice, the chances that you get a total of 6 is about 0.139 or 0.14 if you prefer 2 decimal places. Well, let's do the other one. How many ways can you get a total of 7? 1 and a 6, 2 and a 5, 3 and a 4, 4 and a 3, 5 and a 2, 6 and a 1. Now you add them up, there's 7 of those out of 36. And by the way, I can't count. There we go. There's 6 of those. 1, 2, 3, 4, 5, 6, right? There are 6 of those. And that comes out as 0.17. So can you imagine if people were just inventing gambling games? You roll 2 dice and everybody gets to pick a number. I think most people intuitively would say, well, I'm not picking 2 because I can tell that ain't happening very often. But can you see that there might be a little grey area in the middle where you don't really know, is a 6 more likely to happen than a 7? But if you have the edge on you, won't you always pick a total of 7? Because you're going to beat the other guy. And the game could be quite boring. You keep rolling the dice till one of those 2 happens and then you win your money. Now, when casinos and anything to do with gambling figure out how much money they're going to pay out on a certain event, they will pay out on 2 ones, right? So we're playing that game. They'll give you a lot of money. We'll give you 12 times what you bet. But the reason they're going to do that is that happens 1 in 36 times. So can you see that they're going to be getting money 35 times and only paying out once in every 36 times? And that simple calculation is what keeps Vegas going. They know the chances of everything that they gamble, what the percentage of time that person is going to win, And obviously, what percentage of the time that person is going to lose? Well, let's do complements. If I said to you, what's the probability that you don't get a total of 6? Well, couldn't I just go through this table and count all the different ways I didn't get a 6? Or couldn't I just realize that all I need to do, what was a 6, is take that away from 1, and I got my answer. So it's easier to do. Isn't it sometimes easier to do the opposite of an event than it is to do the event itself? And subtract that answer from 1, and you've got the guy that you're looking for. Are we cool with that? So that's what we talk about. That's what we mean when we talk about the complement of an event A. Any questions? Okay. Next topic is called the law of large numbers. Don't write this down. I'm never going to ask you, and I'm sure the book won't either. But actually, that has got another name, the law of large numbers. It's a name that we use back home, at least. So here it goes. It's called the empirical phenomena of statistical regularity. I'm not making that up. It's the empirical phenomena of statistical regularity, also called the law of large numbers. Can you see why it's probably called the law of large numbers rather than the name I just gave it? And it is a very simple concept. It basically boils down to this. There are two different situations where we look at probability. One side is theoretical. The theoretical ones is the ones we've just been doing. I roll a dice, what's the probability I get a 6? I roll a dice, what's the probability it's an even number? I throw 2 dice, what's the probability that I get a total of 6, right? Those are all theoretical because don't we basically say, look, we know the total number of ways things can happen, and each one of those totals is just as likely as the other, right? And by doing that, we can get them. So that's things like dice. Oh, a very common one is coins. And one that I haven't dealt with, but I'm sure I'll pick some questions later, on cards. You know, when you're playing cards, what's the probability you take a card at random from a deck of cards and it's a heart? Or it's a king? Or, you know, whatever the storyline. And in the next section, what's the probability that you do 2 kings, right? 2 cards in a row and both are kings. You know, those are theoretical. You can actually get the probability without physically doing anything. You just know the bottom number and the top number and you're good to go. And then you've got this other situation. This is experimental, sometimes called empirical. And in these situations, the probability that you're getting is really an estimate of what we believe the correct probability to be. So you know that when they tell you things like there's a 30% chance it's going to rain tomorrow, you know, something like that. What does that look like? How do they come up with that number? Well, they come up by collecting data in various ways. I'll give you an example. Let's suppose for the last 100 years, they've collected data on whether it rained or didn't in Washington State, right? In Bremerton even, right? And out of those 100 years, we're only talking about today, which is, God, what is today? October the What's today's number? It's not meant to be a trick question. I forgot it.
14th.
14.
Say again? 14. Okay. So they looked at October the 15th, tomorrow, right? And of those 100 years, October the 15th, 22 times it was raining. So the empirical probability is called the relative frequency, which we've seen that word before, right? And what would it be? Well, it would be 22 out of 100. We have got 0.22 or 22%. So the guy on TV or the newspaper or wherever it is you got that, this would be his prediction on the probability it rains tomorrow. And he's basing it on the fact that over a long term, about 22% of the time it rained on October the 15th. Now, tomorrow it might rain. Tomorrow it might not rain. Isn't this just giving you a number on how likely it is, right? If I said it was 82%, you'd probably bring an umbrella. If I said it was 2%, you probably wouldn't, right? I mean, so you've got a gut feeling on big, very likely. 50%, yeah, it's a coin toss. Maybe I'll do it. Maybe it won't. And 2%, 1%, yeah, it's not going to harm. You get surprised, but it could. Now, what does the law of large numbers says is that if you do this number big enough, then this relative frequency, whatever it is, will start becoming the real true probability. I mean, technically, isn't this just an estimate? If I had 200 years of data, wouldn't it be a better estimate? If I only used the last 4 years, wouldn't it be a very crude estimate? It wouldn't be very accurate. So I'll give you a story connected with that. Let's suppose I didn't know that the probability of getting ahead was 0.5, right? Theoretically, would you agree 1 out of 2 is 0.5, right? Let's suppose I didn't do that. Then I might do this. I get someone to throw a coin 100 times, and we get them to find out what the relative frequency for the heads was. And the answer they got was 0.52, which in other words, 52 times it was heads. Now, that is not a contradiction of this. When you throw coins in the air, don't you sometimes get a few more heads than maybe the probability says? Because that's, for want of a better word, isn't that chance or luck? Couldn't you just be freakishly lucky and get 90 heads out of that 100? Well, assume you're not cheating in any way. So he does it a second time. He pays this guy more money because it's going to take him longer. And he says, okay, throw it 1,000 times. I want to see what's going on here. And he does it again. Only this time, he gets 0.497, which meant, what, 497 heads. Is that a contradiction that the answer should have been 0.5? No. Couldn't you throw 1,000 times and get a little bit different than 500 each? In fact, it's in a funny sort of a way, isn't it more likely that you won't quite get 500 each? You're more likely to get a couple too much or a couple too little because there's more chances of that happening. Now, if you did it 1,000,000 times, what the law of large numbers says is that this answer will end up being so close to that number that it matches it. Right? If you physically could do it, if you threw 1,000,000 coins in the air, right, all at once, and then you counted how many heads there were, it shouldn't surprise you that it's probably darn close to being 50% of the time. Now, when you've got 1 million coins, can't you be 500 out? But isn't 500 out over 1 million a tiny decimal? It doesn't make a lot of difference. So that's basically what the law of large numbers says. If you do something lots of times, the relative frequency approaches what the theory is. Now, if you don't have a theoretical answer, can't you use this as your way of telling what you believe the true answer is? Now, I'm going to show you. What's called the Monte Carlo fallacy. People use the law of large numbers and they use it wrongly. They use it so that it sounds like it's going to tell them what's going to happen. Probability doesn't tell you for certain what's going to happen. It just tells you the chances of various things happening, right? So imagine a guy was playing a coin game and he threw the coin 100 times, or he was going to. And by the time he got to 99, he found out that that's just happens to be the way it came out, right? So his 99th throw, this is what he's got. So he's thinking to himself, one more coin to go, right? And the Monte Carlo fallacy says that people think that the last coin is more likely to be a tail than it is a head, because you think that these should balance at 50-50, right? Because that's what you expect from the theory. What is the chance that you throw that last coin and get a tail? Is it better than half? Less than half? Or is it still 1/2? The last coin thrown there, what's the probability it's a tail?
Still 50-50.
Still 50-50. Now, why does that cause problems in gambling? It's not uncommon for people to do this in roulette, is why it's called Monte Carlo. They play roulette there. One of the bets you can do in roulette is you can bet red or black. It's equivalent, almost the equivalent of head and tails. They have a thing called a green zero or a double green zero in some places, but it's red or black. And what happened in the Monte Carlo fallacy is that people watch the roulette tables. In fact, the casinos will do this to try and encourage people into this mistake. They'll tell you it was a red number, a black number, a black number, a black number, red. Can you imagine that there was 20 black numbers in a row? So here is the gambler watching this. 20 blacks in a row. Shouldn't you get roughly the same number of black numbers coming up as the same number of reds, right? They're equal. And so he will go and he will go and he will grab all his money that he can get his hands on and says, I know what's going to happen. Shouldn't the next one be a red? It's time for things to balance out. You can't keep having black. I'm going to bet all my money in the red. And he goes and bets all his money. And he has a 50% chance of winning, which he had anyway, and 50% chance he loses. Because isn't the next number being black or red exactly the same as it was before he even looked at this information? It has no effect. And the other group, they say things like, hey, black numbers are hot tonight. I'm going to keep betting black because I'm winning. Isn't the chance that the next number is going to be black exactly the same as well? Probability does not tell you what's going to happen next. It never has. People think it, maybe they falsely think that, but it never does. What it tells you is the chance of that thing happening. So if you're a gambling person, do not fall for the, oh, there's an awful lot of black numbers happening, or they're rolling 2 dice and the total 11 keeps happening a lot. Don't think of that as being anything but just the randomness of what happens in real life when you do things that have a variable chance of happening. Okay, I'm now going to show you, if I can, some of the homework questions. Right, anybody in chat I need to know? Okay, I got you, Hannah. I'm sorry to hear that. Okay, so darn it, I got the things always set up to do hints. I hate those things. They distract the heck out of me. Okay, no, try again. Okay, suppose the newspaper says the probability of rain today is 15%. What is the complement of this event?
50.
Oh, you're right. It is, well, let me rephrase that. What's the complement of the event rain today? Which one of those four statements means the same thing?
We're not looking at the homework.
I didn't do it right? Oh, sorry. Are you looking at it now? Yeah.
I can see it now.
Okay, I don't know what I did wrong there. Here goes. Okay, so what's the complement then of the event it's rain today?
No rain today.
There we go. If this is 15%, would you agree this is 85%? But since they want the answers to 2 decimal places, you will have to convert your guy into that. They just like decimals. I guess the book or the WebAssign handles decimals better than percentages or fractions. What's the event? What's the probability of an event that's certain to occur? Covered that. Something that's certain, what's its probability?
1.
And if it ain't going to happen, it's 0. Agreed? Here's the thing about the law of large numbers, so I'll let you worry about that. Now, this is relative frequency. In other words, we're not doing theoretical probability, we're doing an experiment based on some data. And it's a relative frequency that we're interested in. So in a recent survey of 1,070 adults, 629 said that firefighters were a very prestigious job. And let's see what that comes out to be. 629 then gets divided by 1070, and you type in your answer to the nearest 100th, which according to my calculator is 0.59. I mean, it takes me longer to describe what's going on than it does actually do the homework, doesn't it? I mean, see how quick this is. Right, now, suppose you have 4 children, boy, girl, girl, boy, right? All those combinations. This here is the sample space. All the different ways in which you could get males and females in a family of 4. Now, what's the probability that 4 children are male? Well, if you count through this, can you trust me that there are 16 choices? So what's the probability that all 4 are male? Well, won't that be 1 divided by 16? And then you figure out what that is as a decimal. What's the probability that you get 2 females and 2 males? Well, 2 females and 2 males would be that one, right? Would be that one. Would be that one. This one. Hope I don't miss any. Isn't that 6 out of 16? Now, what about this fella? Notice that the complement of the event, all 4 children are male. So the opposite of all 4 children are male is at least one of the children is female. Now, if you were thinking logic, doesn't that make sense? All 4 are male, what's the opposite? At least one of them has to be a female then. Wouldn't that be the opposite event? At least one of them has to be a female. Could be 2, could be 3, could be all of them, right? But at least one. Use this information to compute the probability that at least one child is a female. What fraction is that then?
15/16.
See how it's easier to count by doing the complement, right? 1 is, 15 isn't. That's essentially what's going on there. There's a probability. Here's a list of ones that don't work. There's 4 different choices. Give me one that doesn't work as a probability. Maybe make it a little bit bigger. Don't know how big your screen is.
A, B, and C.
C, is that one that doesn't work? Great. So the reason it doesn't work is that it has to be between 0 and 1, and right, 120% is bigger than 1. So far, so good. Right. Now, here is a table that's collected probably by a social scientist, and what they did is they looked at married couples, and in particular they looked at personality types, things about their personalities, and they, you know, partner A had these personality traits and partner B had these different ones, and then they just counted how many they shared. And here, there are only 4 basic ones. 30 married couples shared all the same personality traits. So I have no idea what they are, but I'll pick up ones. Maybe one is very structured and the other is carefree, right? Maybe that's a personality trait. Maybe one is conservative in their outlook, one is liberal in their outlook, right? Can you imagine these are various persons? One tells jokes, which I do, and one hates jokes. That wouldn't be a good partner for me, but my wife actually, I don't know if she likes my jokes. Celeste, do you like my jokes? I'm shouting at my wife. Celeste, do you like my jokes? The answer was, if you didn't hear it, not really. So I guess we don't share that personality trait. So anyway, focused on it. Let's look at what is going on here. So if you wanted to actually create this table here, which is called a probability distribution, you need to know. Let's look at people who have one trait in common. Then wouldn't the answer be 68 divided by 375? And if I did 68 by 375, 68 divided by 375, I get about 0.18, which I'm going to put down here, right? Now, a social scientist might look at this data, and I would expect they'd come to a conclusion that the people tend to get married to others who share a lot of common traits, but they don't like getting married to someone who's like a male version of them or a female version of them, right? They like at least something to be different. Because if they liked everything to be the same, wouldn't this last number be really big? It'd be in the hundreds as well. So 3 or 2 seems to be good. And would you agree that they don't tend to, there are exceptions, but you don't tend to marry someone who's totally different personality from you. I don't suggest that you go reading data on what those personality traits are, and then when you get your partner, decide to dump them because, oh, well, we are too much alike, and that's not the way this is meant to be, and so I'm not marrying you. I think evidently for those 30, it was very successful, right? It's just the data. Right, now, if you roll a single dice, number of dots on top, which one of these would represent what we are talking about, the outcomes, the sample space? And the answer is that one. Would you agree that when you roll a dice, it's a 1, 2, 3, 4, 5, 6? And isn't a 1 just as likely to turn up when you throw a dice as a 2? They were designed that way, right? To just randomly roll. Now, what's the probability that you get each of these? Each one of these, isn't it going to be 1 out of 6? There's a question. What would you get if you added up all these probabilities? Yeah.
1.
You get 1. Wouldn't that cover every possibility? The chance of getting a nothing, or a 1, or 2, or 3, or 4, or 5, or 6, they all add up to 1. Here's another empirical one. I won't do the probabilities here, but you can imagine what you're going to do here. You're going to take this number and divide it by the total, whatever it happens to be. If I just look at the raw data, the thing that I find interesting is the time at which inventors said their best ideas, you know, about the new invention or an improvement on one that's already there, happened between 6 o'clock and midnight. I'm assuming this data is good stuff because it's from 966 inventors, and US Today is reputable at least. So if I think about research and development, which is where inventors kind of do their job, that's where they work. Unless you're a freelance, right? You just make your own inventions and, you know, sell them. And you probably work in an office until COVID came. And don't offices kind of 95? Oops, sorry. Go away. Apologize. Where was I? Yeah. So do you know if I was running a big tech company, do you know what I would say to my inventors, the people who have the bright idea guys? Don't come into work. Stay at home. Have fun. And sometime tonight when a good idea comes to you, email me. In a way, wouldn't that be a better work system if you were hoping to get inventors giving you good ideas, right? Because, you know, if you work 9 to 5, you probably don't want to go home and keep working again, right? That's like a 24-hour job. So can you imagine all the good ideas that never made it because people just, you know, I've finished with work, I'm going home and watching TV instead. And that was me. And we'll let you figure that one out. It's quite a complicated one. And I'll finish with question 12 and then we can move on to the second section. 12 is very like 11. So let's see what the story is. John runs a computer software store. Yesterday he counted 131 people walked by his store. Okay. 62 came in. And 27 of those ended up buying something. And we're being asked to calculate certain probabilities based on this data. So this is empirical again. So the first question, A, from number 12, says, estimate the probability that a person walks by the store will enter it. So the probability that you walked by the store was 131, but only 62 of them entered it. You agree? So the chances that somebody who walks by actually comes into your store is those 62 out of the 131 that walked by. And I'm turning this into a decimal. And they want the answer to 2 decimal places, so about 0.47. Now question B says, what's the probability that a person walked into the store will buy something? So let's see. Now, you know that they who walked into the store, that's these ones. And that's how many bought it. So the probability of that event is 27 out of 62. And that's about 0.44. Question C, what's the probability that a person who walks by the store will come in and buy something? Now, the only difference between those that came in and bought something and those who walked by and bought something is, you notice that the bottom number is now different. 131 people walk by, and that's how many bought, 27. 62 come into the store, and that's how many bought. And if I do this one, I get about 0.21. And then D says, what's the probability that someone who walked into the store, so that's 62, doesn't buy something? Well, if that's how many did, wouldn't that be how many didn't? Well, before I leave this question, let's see what you might be able to get from this. I think that the fact that only 131 people walked by his store is not a very good walk-by rate. I mean, we'll assume that the only people who are even going to bother coming in to buy something are people who actually walk by the store, right? If you drive by it, it's like, well, if you drive down the street, don't you see 100 stores? You're never going to go into them because you're driving by them. Now, if you're walking by one and you say, well, yeah, I like that, I think I'll go in and see how much it costs, you might buy it. So my opinion is that he's probably in a bad area for getting good business. So, you know, the prime real estate is always where there's a lot of walking traffic, right? You don't want to have a store that's up a side street in the middle of, you know, a street full of garages and fire stations, right? How many people are even going to find your store, right? Probably not a good place. He got about a big chunk of people came by, right? Almost half the people came in. That's a good sign, isn't it? He's probably selling good stuff. Yeah? If he could double this, couldn't he get twice as many of these? And if he could get twice as many of these, couldn't he probably twice as many of these? So if he was trying to improve his business, wouldn't the best way, I would think, based on the data I see, is find some way to get more people to come by your store? Now, sometimes that can be dead simple. Do you know if your store is a little bit hard to see, shouldn't you put a big bloody neon sign that flashes lights and goes zzz, or whatever the city allows you away with, right? Or couldn't you stick a big poster before you go round the corner saying, hey, my store is round this corner, it's really good, come and have a look. You know, just try and get your numbers up. And that's what I would suggest. So we are now going to, that's us finished the first one. We're going to get a kind of head start on the second one. So if you give me just a minute. While I'm doing that, why don't you just say hello? We'll get that done right now. So let's get attendance sorted out and just say hello. And that'll give me a few moments to get the next thing up and running.
The last or the next homework 4.2 is timed.
It shouldn't be.
Okay, I think I didn't look today, but yesterday or the day before when I was on it said it was a timed homework.
I have no idea what happened. Is that what others found out?
Yeah, it was saying
Yeah.
that for me when I was checking it like last week.
It still is right now.
Yeah.
Okay, I will fix that. I don't know. It must have been just when I was setting it up. I ticked a box that I didn't mean to tick. It shouldn't be timed. It's just a normal.
Okay.
You know, you got until Sunday midnight, just as everywhere. But thanks for telling me. I'll check actually with both my classes because maybe it's only this class because the other class never mentioned it. But that might mean they never looked at 4.2 as well. So I should double check it anyway. Okay, so I've got it set up. We're just getting, we won't get this finished today. This is what we'll finish on Friday. But at least we'll get a head start on it. Try to find the right buttons. Okay, so here we go. Let's look at what is called mutually. Try to spell it right. LLY, mutually exclusive events. So here's a definition for you. Two events are, I'll use the letter ME so that way I don't have to panic over spelling mutually exclusive. Normally when I spell things wrongly, I just tell people that that's how they spell it in Scotland. And you're all so nice that you just believe me. The real answer is I can't spell. Right, so two events are mutually exclusive if they do not share any common events. So let me give you an example of two events that are mutually exclusive. And I'm going to do cards, because cards are actually very good for these kind of stories. Do I need to spend a little bit of time just going over the structure of a deck of cards, or are you all familiar with it and I can just jump into the question? Okay, here goes. Event A is you pick a card and you get a king. And event B is you pick a card and you get an ace. Those two events are mutually exclusive. Would you agree if it's a king, it can't be an ace? And if it's an ace, it can't be a king. Does that make sense? So these are mutually exclusive. Here are two events that are not mutually exclusive. A is a king and B is a red card. Now, why are they not mutually exclusive? Well, aren't some kings red? In particular, the King of Hearts and the King of Diamonds. Do you see that these two share some events? That makes sense? So mutually exclusive, if you're one thing, you cannot be the other. Not mutually exclusive says you could be one and at the same time, maybe part of the other, right? There's an overlap, at least an overlap, right? Now, how can that affect probabilities? Well, suppose I went and said to you, what's the probability you check one card, right? And you get a king or an ace? Well, there are 52 cards in a full deck. This is why you have to know what a deck of cards is. How many kings are there in a typical deck of cards?
4.
And aces?
4.
And so the answer to this question would be 8 out of 52. Now, I could turn that into a decimal percentage, but for time being, I'm just going to leave it like that. Now, what about the probability that you get a king or a red card? Well, this is what you can't do. There are 4 kings, and I'm going to add to it 26 red cards. Because, right, there are 13 hearts and there are 13 diamonds. That number is 30 out of 52, but that is not actually the right probability. And because essentially, haven't I double dipped? Haven't I counted the same card twice? I've counted it as a king, and then later on I'm counting it as a red card. And that it's not 2 cards, isn't it? The same card, right? It's the King of Diamonds and King of Hearts. So haven't I overcounted by 2? And so the correct answer to this one is 28 out of 52. So do you see that if 2 events are not mutually exclusive, doesn't that make counting the top a little bit more complicated? Because not only do you have to count how many of each, don't you then have to subtract the ones you've double counted? Now, we use this funny word or. It's not me just putting it in for English purposes. It's actually a physical capital letter word or that they use in probability. And it means one or other or both kind of thing, right? That's what it kind of comes down to. And then there's another word that you're going to see, and it's the and word. So let's show you what that one looks like. If you're a king and you're red, how many, another way of saying that is, how many red kings are there?
2.
2. Do you see that that number matches this one exactly? Because isn't the word and just another way of counting the double counters, the ones you're counting twice? Right? 2 red kings in this case. So when you put this together and you do it in a general way, the probability that you get A or B, well, that could be any events at all. It's the probability of A plus the probability of B, take away the probability that is A and B. This is a formula that we use. So let me apply it to this question. What's the probability that it's king or it's red? Well, that becomes the probability that you choose a king, added to the probability that you choose a red, take away the probability. Since I don't have room, can I just say both as a shortcut? What I really should be saying is king and red. Now, there are 4 kings out of 52. There are 26 reds out of 52. And there are 2 cards that are red kings. And when you stick them all together, because they will share the same common denominator, do you see that we now get that calculation I had earlier? So what that is going to allow us to do is calculate probabilities of certain events where there's some kind of interaction between what they might be. So, are we cool with that so far? We're good? Okay. Last chance. Let's do some more cards ones. What's the probability that you get a 10 or a club? Now, the way I do the formula is I just combine them into a single thing, right? How many 10s are there in a deck of cards?
4.
Great. 4. How many clubs are there in a deck of cards?
13.
Try again.
Is it 14?
13.
Oh, 13.
4 suits of 13. Okay, and the last piece of the puzzle is you then take away the both. How many 10s of clubs are there? It's a kind of silly question in a way. They're just 1. So you put this package together and you get, where that came from, 16 out of 52, which almost certainly the book's going to say to so many decimal places. So let's try that out and do a 16 divided by 52, and I get about 0.31. So if you were playing a card game, and let's say you're playing poker or whatever, and you need a 10 or a club to win, right? So when they play the game, they turn over a card, right? If a 10 turns over, you're going to win. If it's a club for a different reason, right, you're going to win. And you're going to say, oh, I wonder what my chances of that happening. You're going to win about 31% of the time, or at least that's the event is going to happen 31% of the time. Now, still on cards. There's a card called a face card. It gets used in some gambling games. They describe it that way. A face card is a jack, queen, or king, right? So if you're a face card, jack, queen, or king. If you wonder why it's called a face card, if you get a deck of cards and look at it, doesn't the jack have a face on it? Queen's obviously got a face on it, so does the king. So that's why they're called face cards. So what's the probability that you get a face card or a black card? Okay, how many jack, queens, and kings are there in a full deck of cards? So you have to do a bit of counting here.
12.
Right. 3 from each suit, 4 suits, 12, right? Something like that. How many black cards are there in a deck of cards?
26.
26. Take away both. How many face cards are black face cards?
6.
So you put this package together, I believe you get 32 out of 52. And as a decimal then, 32 divided by 52 comes out as about 0.62. Would you agree if I needed a face card or a black to win, any kind of black card to win, then aren't I twice as likely to win as this guy up here? So people who play card games, like professional gamblers, they have to be, I don't know how they can't be and be successful. They have to be able to do these on the fly. They have to be looking at their cards and saying, okay, what do I need to beat this guy? What's my chances of beating him? The other guy saying, what do I need to win? What's my chances of beating him? If I was a poker player and this was my hand, right? This is what I needed to win, right? Wouldn't I bet on this? Because I'm more likely to win than I am to lose. If this was my chance of winning, wouldn't I maybe just fold? Better to lose a little money than gamble more and lose it, right? So you see, those are the types of decisions that those kind of people would make. If you play a very simple game, blackjack, you can look at your cards that you've got and then you can say, what's the probability that I get this card? And if it's better than 50%, you should probably go for it. And if it's not, you should probably, just say, I'll stick. And so gambling games, especially card gambling games, are quite, use this idea a lot. I am not promoting gambling, by the way. You will lose money, guaranteed, if you go to Vegas and do any gambling game. I go to Vegas because I like Vegas. It's fun. But I don't go to Vegas to win because I very rarely do. We go. Next topic. We're going to look at what's called conditional probabilities. You will see it written using this notation. You read this out loud as the probability that A happens. This funny little vertical line represents given that event B has already happened. So the probability of A given B is how you typically say that shorthand. The probability of A given B. This is it in full English. In, I guess, shorter version. Probability of A given B. show you what that looks like. What's the probability that you get a 6 when you roll a dice?
Out of 6.
Okay, which we round to a decimal, 0.17. What's the probability that you get a 6 given that it was an even number? Suppose someone could look into a crystal ball and they can't quite see exactly what happened, but for some way or some method or whatever you want to call it, they found out it was even. Hasn't your world now changed as far as the chances that you've got a 6? You know that it's even. So doesn't that mean that the bottom number is only 3 numbers now? You take this B as being a given event, right? Something that is true. So if it's true that it's even, there's only 3 of those. And one of those is a 6. On the other hand, if I said to you, what's the probability that you get a 6, given that you know it's an odd number that happened? Well, there's 3 odd numbers. Unfortunately, none of those are 6s. Do you see that these 2 conditional probabilities are quite different from each other? Some information will improve your chances of winning, and won't other information make it much harder, if not impossible, to win? Agreed? So conditional probabilities are very often used when you want to find the probability of something happening, but you've been given a little bit extra information about it. So suppose I give you a card question again. And I say to you, what's the probability that you get a card and it's a king? Well, that's 4 out of 52. Pretty unlikely. Happens now and again, but pretty unlikely. This is going to be my last question today. And that comes out as about 0.08. About 8% of the time, you're going to get a king. What's the probability that you get a king, given that somehow or other, you were told that it was a face card that was about to come out? Well, remember the face card was Jack, Queen, or King? And I believe if we did that, wasn't there 12 of them? And how many of those 12, so it has to be this number here, how many of those 12 face cards are kings?
4.
And so we are now looking at a much higher chance. What about this one? What's the probability of getting a king, given that it was a red card? Now, the chance of me just getting a king with no extra information is about 8% of the time. I wonder what the chances of getting a king being told that it's a red card. Do you think that might help, hinder, or make no difference? Raina, you got an answer?
I think it's gonna make a difference, but it's gonna be very little.
Okay, let's see what happens. Yeah, it could be. We got red cards. How many red cards in the deck?
26.
26. Now remember, only count the red cards now. In the red cards, how many are kings?
2.
And guess what? Can you see that some information is useless? It doesn't change anything. The probability of getting a king is 0.8. The probability of getting a king knowing that it's a red card is exactly the same. We have a name for 2 events where this event and that event are the same thing. We say that these 2 events are independent. So an event is independent if the probability of A given B is the same answer as just the probability of A. We say that those events are independent. I guess in English you would say one event has no effect on the other. Now in the medical world, independence is quite interesting. The opposite is probably more interesting. The opposite is when they are dependent. So these, for instance, are dependent. Doesn't this affect the answer? Some things, the dependence one on the other affects things in a bad way, and sometimes they affect things in a good way. So to give an example of dependent things. Isn't overweight and your likelihood of having a heart attack connected? The more overweight you are, the more likely you are to have a heart attack. Those would be dependent events. If you are blonde hair and you'll get a heart attack, would you agree that they have no effect on each other? Blonde people get heart attacks just as much or as less, I'm assuming, than any other colored hair person, right? Those would be independent events. When you're in the medical world, you're not really worried about the independent events because don't they tell you nothing, right? You're with blonde hair, I'm not going to change anything, right? You're just as likely to get a heart attack. But you would look at things like, which ones are dependent? And then even within that, wouldn't you sometimes try and put a hierarchy and say, high blood pressure is the worst of the lot. Overweight is the next worst. Family history is the third one, and maybe I can't think of a fourth one, but whatever it is, too much potassium in your body, right, is the fourth one. And what would doctors do then is that those dependencies, wouldn't they influence the risk of that particular person getting, say, the heart attack? And so how do you reduce the risks? Well, don't you go for the ones that are the most dependent? Okay, let's get that blood pressure down. Here's medication for it. Let's put you on a diet. Let's get some of that weight off you, right? Go through the list, and the more you can reduce those factors, won't you then improve the likelihood that that person won't get, that's a double negative, but you reduce the chance that a person gets a heart attack. And we have all sorts of medical data on simple things like, I can't tell you numbers because I don't know off the top of my head, but I'll make ones up. For people who are morbidly obese, they're 20% more likely to get a heart attack than those people who are on, the optimum weight level. Those kinds of things. Well, you say, where's those 20% coming from? They're coming from these kinds of calculations. What's the probability of a heart attack given you're obese? What's the probability you have a heart attack given you've got normal weight? One of them's 20% higher than the other, and that's where that data comes from. It's all empirical, right? You collect data on heart attack patients and what weights they are and things like that.